Hello everyone, this is lecture 17 on fixed point theory. Today I am going to explain a closer look at L1 and stability results in arbitrary spaces. Now the first topic is a closer look at L1. Now what do you mean by L1 space? It is a space whose elements consist of all the absolutely convergent sequences of real numbers. Now absolute convergence means the series mod of xi, this is convergent, right? And here the distance between the two sequences is defined like this. It is the series mod of xi minus yi, where I varying from 1 to infinity. So we have L1 space which consists of all absolutely convergent sequences of real numbers. Now the next space is space C. It is a Banach space of all sequences of real numbers which converges. So it is a space of containing all the sequences of real numbers which are convergent. So it consists of convergent sequence of real numbers. And C naught, it is a subspace of C which consists of those sequences which are converging to 0, right? So C naught, it contains all those sequences which are converging to 0, and here the norm is defined like this. So clearly C naught is a subset of C, right? Now the next, if we have a bounded sequence in L1, then we can say this thing, that a bounded sequence in L1 is weak star convergent relative to the dual space of C naught, which is L1, if and only if it converges coordinate wise. Dual space means it is a mapping going from continuous and linear functional subspace, right? So the dual of C naught star is L1 space. Now the lemma, this says if we have a bounded sequence in L1 which is weak star convergent to X relative to the dual space of C naught, which is L1, then for any Y belonging to L1 we have this relation, right, where Ry is what? Ry is the maximum distance of the sequence xk from Y, right? So we find out the norms of xk minus phi, and we find out the supremum of all that, and then we find out the limit, and that value is denoted by Ry. So this denotes the maximum distance between xk and Y, right? So what this lemma says, we have a bounded sequence in L1 which is weak star convergence relative to X, right? It converges to X relative to this space L1. Then for any Y belonging to L1, the Ry is equal to Rx plus norm of X minus Y. For the proof, we consider the standard unit basis for L1, and these are E1, E2 and so on. What do you mean by E1? At the first place, the value of this number was, first coordinate is 1 and rest all are zeros. E2 means at the second place, second coordinate is 1 and rest all are zeros, and so on. This is the standard unit basis for L1. Now we consider Pi. For each I, we consider Pi, which is a natural projection of L1 onto its subspace spanned by E1, E2 till up to EI. So what do you mean by Pi, x1, x2 and so on? It means at ith place we have to take the projection, we have to take the same values and rest all are zeros, right? Qi, it is a complement of Pi. So Qi of x1, x2, x and so on means all these are 0 coordinates before xi plus 1, and the tail is same, right? So here we are having x1 till up to xi, they are same, and rest all are 0. So means P1 means what? Means x1 and rest all are 0. Okay, so Q1 means what? 0 at the first place and rest all are x2, x3 and so on. So basically this is a complement of Pi. Now what is Rx? So by definition, it is a norm of xk minus x. Take the supremum and then take the limit k going to infinity. So we have to take limit supremum k going to infinity of this norm, right? And which is same as that, since our k is going to infinity, it means it is a tail elements, right? So that is same, we can write, this is basically the tail. So we can write this is a sequence qi xk minus x. So rx is our this thing. Now since pi of xk minus y is what, its norm is basically the mod of xk minus y, and here our n. So if we take it in depending on n, here our n is varying from 1 to I, because it is pi, rest all are zeros, right? Then we have the norm of x minus y. It can be written as the norm of pi xk minus y. Take the limit k going to infinity, so it contains all these elements, and then take I going to infinity, so that will become your norm of x minus y, right? So when you take k going to infinity, we have to consider all the sequences, all the differences, and when you take I going to infinity, it means all are the projections, no zeros here, right? So this is same as that norm of x minus y. So here it is basically not yn, it is y, not yn. Here it should be y, right? Also the limit of qi on x minus y, this norm, when I going to infinity, it is what? It is the mod of xn minus yn. So the coordinates of x are x1, x2 till up to so on, and since we have to take the tail, so our n should start from I to infinity, right? And our I is also going to infinity, so basically it is a tail element. So this is mod of xn minus yn. So here this n denotes the nth coordinate of this y, basically. So it is yn, not y, it's yn, right? So since this is a tail, okay, so it will goes to 0. All these are tail, right? So this goes to 0 because we have a sequence, this is belongs to c0, so this is converging to 0. This is a tail, so this is going to 0. So now take the norm of this plus the norm of qi xk minus x minus the norm of qi x minus y, right? So we can combine these two. The norm of a minus norm of b will be less than equal to, you can add it, norm of a plus b. So we have this, basically the point xx will be cancelled out and you left with this. So clearly this should be less than equal to this number, right? And these are first I element, these are after I element, so you can combine these two. So basically this is the norm of xk minus y, right? So what we get, this is less than equal to the norm of xk minus y. So when you take k going to infinity and I going to infinity, what you have, this is nothing but ry, okay? And this term, when you take I going to infinity, this is 0 from here, and this term will become your rx in the previous slide, right? And this is what, when you take I and k both going to 0, this is nothing but the norm of x minus y. So we can replace this with norm of x minus y, this with rx, and this with 0. So what we get, norm of x minus y plus rx is less than equal to ry. So this On the other hand, the norm of xk minus y, when you add x and x, so it will be less than equal to this. Now when you take k going to infinity and I going to k going to infinity and take the supremum one, what we have, this is nothing but rx, and this is norm of x minus y, and this is ry. So we get ry is less than equal to rx plus norm of x minus y. But here we are having the reverse inequality, so combine these two, we have these two are equal, and this thing we have to prove. So this proves the lemma. Now the next is the definition of normal structure. A convex subset K of a Banach space is said to have normal structure if any bounded closed convex subset H of K, for which the diameter of H is strictly greater than 0, contains a point x0 for which the norm of x0 minus x, where x is any member of H, and take the supremum one if this is strictly less than diameter of H. Then the point x0 is said to be non-diametral point of H. Means this point x0 is not lying on the circumference of that circle or sphere, right? It lying inside. So that's why the supremum, the distance of the x0 with every point of H is always strictly less than the diameter, right? So what do you mean by the normal structure, weak normal structure, weak star normal structure? So in normal structure we have to consider bounded closed convex subset H. In weak normal structure we have to consider bounded weak closed convex subset, and in normal structure, weak star normal structure, we have to consider a bounded weak star closed convex subset H, right? So this is respectively. So a convex subset K, and we have written here the possibly conjugate. Possibly conjugate means the dual of K. As we know that the dual of a nonlinear space is a Banach space. So this is a Banach space, and dual is also sometimes called the conjugate. So the dual of this, it should be Banach, right? So convex subset K of a Banach space is said to have normal structure if any bounded closed convex subset H of K, for which the diameter of H is greater than 0, having the point x0 for which this condition hold, and this point x0 is said to be the non-diametral point of H. Now for a bounded closed convex subset K of a Banach space X, R xk, it denotes, you have to consider norm of x minus y, so we have to fix this x and varying y, all the elements of k. You find all the norms and then find out the supremum one. That will denote the distance of, max distance of this point k relative to this x, right? And rk is what, for in this case we have considered, we have fixed this x, now we have to vary x and find out the infimum of all these r, right? So that will be the rk, right? And now let ck, it is a set of all those x belonging to k where rx k is same as that rk, right? It means the points, they are lie on the boundary basically, only then these values are same. Okay, so we have a assertion which says that x has a normal structure, means that for any bounded closed convex subset k of x, in the case that whenever rk is strictly less than diameter of k, whenever the diameter of k is strictly greater than 0, so whenever we have a diameter k greater than equal to 0, strictly greater than 0, rk should be less than diameter of k. If k is weakly or weak star compact, And if X has weak normal structure or weak star normal structure, then CK, it is non-empty, proper weakly or weak star, compact convex subset of K whenever the diameter of K is strictly greater than 0. In fact, this CK is admissible, that it can be represented as the intersection of closed balls centered at the points of K, right? So what is this CK? It is the intersection of C epsilon K, where epsilon is greater than 0. So it is the intersection of the closed balls, right, with taking the centered point of the K. So this is what C epsilon K is, the intersection of all the closed balls with center at X, and the radius is RK plus epsilon, and the intersection with K. So this C represents this value. Now the stability results in arbitrary spaces. This topic is little specialized, but it highlights a metric approach to the stability results discussed in connection with Braud's theorem. So let K be bounded closed convex subset of a Banach space, and T be a mapping going from K to K, which satisfying this inequality for some h greater than 0 and for p greater than 0. So if we take p to be 1 and h to be strictly less than 1, then this is contraction mapping, and Banach mapping theorem is applicable to here, so we have always a fixed point. And if p is 1 and h is also 1, then these mappings are said to be non-expansive. And in case p is 1 and h is greater than 1, then that is usual Lipschitz condition. But if the value of p is strictly greater than 1, then this equation, this mapping is said to be, they are satisfying, they are degenerate, right, whatever the value of h. Okay, but our observation is that whenever h is strictly greater than 0 and p is less than equal to 1, if this mapping satisfying this more general condition, then this mapping is said to be h non-expansive. So what is this condition? The norm of tx minus ty is less than equal to max of h, comma norm of x minus y. So then this mapping T is said to be h non-expansive. Now what do you mean by W continuous? Let MD be a matrix space, D be any subset of M, F be a mapping going from D to M. Then this F is said to be W continuous at any point of the domain if for each epsilon greater than 0 there exists delta which is depending on epsilon, such that whenever our x is belonging to D and the distance between x0 and x is strictly less than delta, then this implies that the distance of f of x0 and fx is less than epsilon plus w, where w is greater than 0, right? Then this function is said to be W continuous, and if it is true for every point of the domain, then we say that this function is W continuous on the domain D. Now W contraction means there exists k belonging to 0 1 such that the distance of tx ty is less than equal to k times distance of xy plus w, where w is strictly greater than 0. Then this mapping T going from one metric space to metric space is said to be W contraction, right? Note that if k belongs to 0 1 and L belongs to k1, then for any xy belonging to the M, this inequality holds, this relation holds, right? This relation k times dxy plus w, it will be less than equal to L times d of xy if and only if d of xy is greater than equals to w upon L minus k, and you can easily verify that. that this relation holds, that this is less than equal to L times d of xy if d of xy is greater than equal to w upon L minus k, and if w is distance of xy is greater than equal to this, then this number is less than equal to L times d of xy. So we have, this is important relation. So this leads to a new definition. A mapping T going from M to M is said to be HL contractive if for h greater than 0 and L belongs to 0, 1, the distance of Tx, Ty is less than equal to L times the max of d of xy comma h. So if you take L to be 1, this is h, this is h contractive, h contractive. When you take L over here, then this is HL contractive. So based on these definitions, we have two prepositions. If T is a mapping going from M to M, which is W contraction with contractive constant K, then T is also HL contractive for such number H and L. Right? So we have basically two cases, either this distance is greater than equal to H or it is less than equal to H. Right? Because W contraction means the distance of Tx, Ty is less than equal to K times distance of xy plus W. And HL contractive means distance of Tx comma Ty is less than equal to L times the max of d of xy comma h. Right? So either dxy is maximum or h is maximum. So if d of xy is greater than equal to h, then dxy will be maximum. So in that case, we have to show d of Tx, Ty is less than equal to L times d of xy. Right? And if it is less than h, then we have to show it should be less than equal to LH. Right? So now just see, if this is greater than equal to h, then you can substitute the value of h this and L this. Now since d of xy is greater than equals to h, right, so by using the star, we have it should be less than equal to L times d of xy. Right? Because in this case d of xy is greater than equal to h means it is greater than equal to w upon L minus k. So in that star inequality, whenever this thing is greater than equal to this number, this should be less than equal to L times. So this is proved. Now otherwise, if this number is less than h, right, then you can replace this d of xy with h. Now k h plus w. Now you substitute the value of h over here and you get this is nothing but LH. Okay. So this kh plus w is nothing but LH. Okay. So we have, whenever mapping is W contraction with the contractive constant K, and for such H and L, T is also HL contractive. Now the next proposition is, if T is a mapping going from M to M, which is W contraction with contractive constant K, then the infimum of the distance of X and its image is less than equal to W upon 1 minus K. So let L be number which belongs to open interval K comma 1, and depending on this L, let's suppose we have a H which is W upon L minus K. Right? Now X is any member of M, and suppose that this distance is greater than equal to HL. So the distance between two consecutive is greater than equal to HL, and this contradicts that we have a Banach contraction principle. This sequence should be Cauchy and it should be convergent, but it contradicts, so it means it should be less than HL, where L is belonging to K1. And this proves the result that uh, when you take n going to infinity, we have this is x and this is t of x, so the minimum of this distance is less than equals to HL. But when you put the max value of L, so this will be less than equal to W upon 1 minus K. But in the above definition, if we put K to be 1, then the result become meaningless, because 1 minus 1 will be 0, so we have infinity, so no use of this result, right? So basically when you put K to be 1, we have H1 contractive mapping, and that H1 contractive is said to be H non-expansive, right? So if T is a mapping going from M to M with K1, then we say this is H non-expansive mapping. Now further see, let K be any non-empty bounded closed convex subset of a Banach space X, and T be a mapping going from K to K which is H non-expansive. For T belonging to 0, 1 and we fix element of K, let it be Z, we can define a new mapping T going from K to K by setting this number. Now just see, when you take the value of when you find out the value of this mapping at Z, what you get? It will be 1 minus Tz plus T times T of Z, right? And when you find out this value at 0, when you take T to be 0, near 0, T going to 0, small t, so when your T small going to 0, this T capital T is going to 1, and when your small t going to 1, then this is same as that T of X, right? So we define a new mapping like this. So we have to show that the infimum of norm of x minus tx, whenever x belongs to k, it is less than or equal to h. To see this, we can consider any two elements of k and we can find the norm of ttx minus tty. Now substitute the value of ttx as we have defined earlier in the previous slide. So substitute over here, you will get this is equal to t times norm of tx minus ty. Rest terms will be cancelled out, and we can take t to be outside from this norm because t is strictly greater than 0, right? So further, since mapping t is h expansive, so it should be h non-expansive, so it should be less than or equal to t times the max of norm of x minus y comma h, right? Now we consider a sequence of this ttx. So we take the difference of the norm of two consecutives ones for n greater than or equals to 1 and for x belonging to k. We have this norm. By using this in above inequality, it will be less than or equal to t times the max of the previous images, the norm of the previous image comma h, and further by induction it will be less than or equal to the previous image, and we can take this max to be outside and t to be inside, t square times this thing, and this t will be multiplied with h also, so we get this thing, and so on. So this difference of two consecutive sequence norm, it will be less than or equal to max of t to the power n norm of x minus tx comma th, right? Now further, t is a number which lying between 0 and 1, strictly lying between 0 and 1, so the limit n going to infinity t to the power n, it will be 0, and k is bounded, and this is true, this above inequality is true for every n greater than or equals to 1, clearly it will be hold for n tending to infinity and for infimum. So what we have, this n going to infinity, it is nothing but x, and this is nothing but tx. So the infimum of the norm of this, whenever x belongs to k, this number is 0, n going to infinity, so we left with only th. So max of th, we will get this thing, right? So infimum of the norm of x minus ttx for all x belonging to k, it will be less than equal to th. But the norm of x minus tx norm, now you can substitute the value of tx in the terms of ttx, you get this, it will be less than equal to t inverse of this thing, right? Therefore the infimum of norm of x minus tx whenever x belongs to k, you can replace with th, tt will be cancelled out, you will get h plus t inverse 1 minus t norm of x minus z, right? But when you take t tending to 1 from its left side, right, this number goes to 0 and you will get h only. So this thing we have to prove, and so this proves the result. So K is non-empty bounded closed convex subset of a Banach space X, and T is a mapping which is H non-expansive, then the infimum of norm of X minus Tx is less than equal to H. So we have this result. Whenever K is non-empty bounded closed convex subset of a Banach space, and T is a mapping going from K to K which is H non-expansive, then this result holds. Right, by using the above, the proof is given above. But if T satisfied the holder's condition, then the conclusion is sharper. Means if this norm is less than equal to h times the norm of x minus y to the power p for some h and p belonging to 0 1, then this is less than equal to h to the power 1 over 1 minus p. Now just see how, since h is strictly less than 1, so by above theorem, right, this is not 0, it is only 1, that by theorem 1 there exists any member k such that this is strictly less than h, means strictly less than 1. So you can find tx minus t square x, it will be less than equal to h times, by the definition, norm of x minus tx to the power p, which is less than h into h to the power p. So here you can write h to the power p also, so you get it is h of 1 plus p. So when you take t2 minus t3, you get this is 1 plus p plus 1 p square, and so on. And when you take n tending to infinity, this is a GP series, it will goes to 1 over 1 minus p. So rather taking only h, you can consider to be h to the power p also. Okay, so again you have the same result. But as we know that h and p both belonging to 0 1, so this number is always strictly less than h. So the minimal displacement estimate of theorem 2, it is better than that of theorem 1, because we have find the more smaller number from which this distance is less. So this is a minimal displacement estimate. So thanks.